All right, in this video, we're going to talk about probability. Let's review some of the language that surrounds the study of probability. First, an experiment. This is a process that leads to an uncertain outcome. Simplest example is if you roll a die, you don't know what's going to happen. You don't know the outcome. So it's an experiment. The sample space is the collection of all possible outcomes of an experiment. Even though you don't know the outcome of rolling a die, you do know that it will be a 1, 2, 3, 4, 5, or 6. So that is your sample space for that experiment. A sample point is an individual outcome of an experiment. So if we roll the die and we get a 5, then that is a sample point. An event is a collection of sample points, that is a subset of outcomes from an experiment. We define the event before an experiment. So for example, we could define event A as a 2, a 4, or a 6, even numbered outcomes. Events can be independent or they can be dependent. Independent events are those where the occurrence of one event does not influence the likelihood of another event. For example, in an experiment where we roll a die 2 consecutive times, the likelihood of getting a particular value on the second roll is not influenced by the value you actually get on the first roll. Okay? The probability, for example, of getting the number 2 on a second roll of the die is the same, 1 in 6, regardless of the number you got on the first roll. So we call these independent events. In contrast, dependent events are where the occurrence of one event does influence the likelihood of another event occurring. And an example of that would be the lottery. You've probably seen this little machine where you have balls kind of blowing around in here and then they'll pop out. So what happens is if we run the lottery machine, let's say there's 50 balls in here, the probability of this first ball coming out is 1 out of 50. But when we run the machine again, the probability of the second ball is actually 1 out of 49 because we've removed the first ball. And then the probability of the third ball is 1 out of 48. And then 1 out of 47 and 1 out of 46. You see, the probability is changing with each subsequent release of the lottery balls. Okay, so we call those dependent events. Now, probability is the chance a particular event will occur. Okay? Whether you say the likelihood or the probability, it's the same idea. It's always a number between 0 and 1. 0 probability means it will not happen. 1 means it definitely will happen. Since the world is all about uncertainties, we mostly deal with values between 0 and 1. The probability of the sample space, however, is always 1. And the sample space is defined by the experiment. Once you say you're going to roll a die 1 time, you know you're going to get a 1, 2, 3, 4, 5, or 6. Moving on, now let's talk about the union and intersection of events. If A and B are 2 events in a sample space, A and B, we have the sample space, then the union A union B is the set of all outcomes in the sample space that belong to A or B. So it would be everything in A and everything in B. Let's use some numbers to illustrate. If we define event A as 2, 4, or 6, an even number on the roll of a die, and we define event B as a number greater than 3, 4, 5, or 6, then the union of A, B becomes 2, 4, 5, 6, because those are the outcomes in the sample space that belong to A or B. Contrast the union of events with the intersection. This says if A and B are two events in a sample space, then the intersection A intersecting B is the set of all outcomes in sample space that belong to A and B. You see the difference here? With the union, it's those outcomes in the sample space that belong to A or B. Here it's those elements in the sample space that belong to A and B. Using the same example, we have 2, 4, 6, and we have 4, 5, 6. Well, what outcomes, elements, belong to A and B? 2 only belongs to A, 5 only belongs to B, but 4 and 6, those belong to A and B. So visually, we might want to actually put 4 and 6 in this middle area, showing that the intersection is 4 and 6. Now, these diagrams are known as Venn diagrams, and they're helpful to give us a visual aid of what's happening, kind of the intuitive perspective. But we do want to develop a mathematical acumen for calculating unions and intersections. And that's where these formulas come in handy. For example, let's say that we want to know the probability of getting a red or an ace. Well, you see the word or there, which implies that we're trying to find the union of red, ace, right? To do this, we use the formula. The probability of A union B is equal to the probability of A plus the probability of B minus the probability of A intersecting B. Let's put some numbers on these. Well, I would rather write this out as R and A. So let's rewrite it as the probability of getting a red union ace is equal to the probability of getting a red plus the probability of getting an ace minus the probability of getting a red intersecting an ace. Now let's put some numbers on these. The probability of getting a red in a standard deck of cards is half the deck. Since there's 52 cards, we could say that's 26 over 52. Right? The probability of getting an ace in a standard deck of cards, well, there's 4 of them, so it's 4 out of 52. Okay? The probability of getting a red intersecting an ace, remember intersection means and, so red and an ace, well, there's 4 aces and 2 of them are red. So in a standard deck of cards, there's 2 out of 52. So we subtract 2 out of 52. Now if you do this, you're going to get 26 out of 52 plus 4 out of 52 minus 2 out of 52. So that's going to be 28 out of 52. So the probability of getting a red or an ace in a standard deck of cards is 28 out of 52. Makes sense, right? Because you have 26 reds and then you have 2 aces on top of that that are black. Now let's do the mathematical computations for intersection. And here we're being asked to determine the probability of a red ace. So you interpret this as red and ace. The formula says the probability of A intersecting B is equal to the probability of B. This line means given that A occurs times the probability of A. Okay? We're going to talk more about this later on, where this is called a conditional probability, the probability that B occurs given that A has already occurred. Also, we could get the same answer by doing the probability of A intersecting B equal to the probability of A given that B occurs times the probability of B. Let's put some numbers on this. Again, I like to rephrase. to fit the question at hand. So I want to say, I'm going to use this one here. The probability of a red intersecting an ace is equal to the probability of a red given that an ace occurs times the probability that a ace occurs. And from a calculation standpoint, we first need to find the probability of a red given that an ace has occurred. Well, if we have an ace, what is the probability of getting a red? And well, there's 4 aces, so if you've got all aces, half of them are red. So it's essentially 1/2. And then the probability of an ace is, well, there's in a deck of 52 cards, 4 of them are aces, so 4 out of 52. Or you can break that down. You could actually say that's 2 out of 26 or 1 out of 13. So we'll put 1 out of 13. Don't have to, but sometimes it makes it easier. Now we can calculate the probability as 1/2 of 1/13, which of course is 1 out of 26. Okay? So the probability of getting a red and an ace, a red ace, is 1 out of 26, which is 2 out of 52, and that makes sense, right? Because there's 2 red aces in a standard deck of cards. Right. Now, what if we had used this formula here? It would give us the same results, right? Let's do it just to illustrate. The probability of getting a red intersecting an ace is equal to the probability of a ace given a red times the probability of a red. Put some numbers on that. The probability of getting an ace given a red, well, there's half the deck is reds. There's 26 reds, and 2 of them are aces. So 2 over 26, or 1 over 13. So 1 over 13 times the probability of a red, which is 1/2. And notice you have the exact same thing. It's just 1/2 times 1/13 here. Here it's 1/13 times 1/2. The result is 1/26. All right, so that's how we calculate an intersection. Next, let's talk about mutually exclusive and collectively exhaustive events. Events are considered mutually exclusive if they cannot happen at the same time. In our Venn diagram, it means that event A is a separate bubble from event B, no overlap. Another way of putting this is the intersection of A, B is empty. There isn't one. Let's imagine, for example, that we take the typical college classroom for economics. So that's everybody, maybe 50 students in a college classroom. And let's say that event A are those students that are aged 21. And event B are those students that are aged 22. Well, you can't be 21 and 22. So we would consider A and B mutually exclusive. Collectively exhaustive events are where the events cover the entire sample space. For example, let's say that the sample space is the US population, and we define A as the event of people that are unemployed. Well, the remainder of the sample space, A complement as it's called, must be everybody that is employed. That makes these two events collectively exhaustive because everybody in the US population is either employed or unemployed. Another example is if we define event A as smokers in the US. Well, the complement of A becomes non-smokers because everybody in the US must either be a smoker or a non-smoker. Okay, that's it for this video. If you have questions, let me know.